So we will have Kirk Sorensen, excuse me if my pronunciation is not the best one, from Flibe Energy, who will speak about the Flibe. Flibe is a
Flibe.
company
Flibe
which
Energy, yeah.
flies in Europe. Flibe Energy LFTR development strategy.
Thank you. Thank you very much. I'm glad to be here today at the third Thorium Energy Conference. I've been pleased to be at the first two. I missed last year. I'm very pleased to see this crowd, which is much larger than in previous years, and I'm especially pleased that so many of you are still here because I am what is standing between you and your dinner. So in view of that and the fact that we are about 15 minutes behind, I will do my best to accelerate my presentation so that we will be able to go and enjoy dinner as soon as possible. I'm going to be facilitated in this task by the fact that so many excellent talks have taken place today that have already covered so many of the points I wanted to make. So I can trim out and truncate a great deal of what I have to say. But let me talk about a few things that maybe haven't been said so much today. Our perspective as a company is the industrial perspective, and when we are talking to those who are generating electricity, these are the things that they're worried about. We are undergoing an enormous wave of coal-fired power plant retirements in the United States, and as you can see, this is particularly concentrated in the eastern United States, where I live, particularly on the Ohio River and in the Carolinas. And this is being driven in large part by new regulations related to emissions from coal-fired power plants. I know that many people are glad we're having these emission regulations, and part of me is as well, but I'm also a little concerned of just how many gigawatts of generation capacity are being prepared to be taken off the grid in the United States. The options for renewable energy, as you can see from the map of the U.S., are predominantly concentrated not in the eastern United States. So this limits our options. There is exciting activity taking place in the U.S. in the nuclear front. In Georgia, 2 new nuclear power plants are under construction at the Vogtle site. These are going to be Vogtle 3 and 4. They're going to be AP1000s. They're being added to an existing site of 2 other pressurized water reactors. So we are going forward with new nuclear power plants under construction in the U.S. Unfortunately, I don't think this is going to be quite enough, because this is a graph that is already a few years old that shows how even with renewals of licenses in the late 2020s, we're going to fall off what we call the retirement cliff. In other words, we're going to be retiring reactors much more quickly than we're bringing them online. And as I said, this is a few years old. This cliff has actually gotten a little worse since this graph was generated. So we need to be in position in the United States in the late 2020s to be able to add enormous amounts of generation capability to the grid quickly. And if it's not going to be coal, what is it going to be? Now, one of the things that I think merits consideration, especially when I'm talking to an international audience, is you have to understand how things work in the United States. Our Department of Energy has a very hands-off approach to how things should be designed and developed. In their opinion, it is the responsibility of industry to design, construct, and operate commercial nuclear power plants. It is industry's decision which commercial technologies will be deployed. The federal government has made it explicitly clear that they don't choose winners in the nuclear space. It's up to industry to go and make a credible case for why a technology should be developed and to go and take the risk to make that happen. They will offer some support in different ways, but it is not, from their perspective, it's not up to them to decide. So considering this, the needs that we're going to have to bring new nuclear power plants online quickly, we are very interested in modular construction of nuclear reactors. In modular construction, we'll be able to build them in a factory. We'll be able to enforce a degree of commonality and quality and uniformity to that. We'll be able to learn quickly from mistakes, rather than the way we've done it so many times in the past, which is in the field construction, where a lot of mistakes can get made. And we feel strongly that liquid fluoride reactors, which are a type of molten salt reactor, with their low pressure operation are particularly suitable to this goal, this hope, this objective of achieving modular construction. because one of the hardest things to get around when you're building a nuclear power plant is the large, heavy pressure vessel that's required when you use pressurized water reactors. So we see molten salt reactor technology as a way to perhaps come closer to realizing the dream of small modular reactors. Well, what kind of molten salt reactors should we consider? And I thought that at this point we would have covered some of the points about molten salt reactors, and in large part we have, but let me make a little bit of a defense for why molten salt reactors. One of the first points is we don't have to fabricate fuel. The preparation of fuel is very easy in molten salt reactors, particularly in the fluoride media. Another aspect is fission product gases are continuously removed by operation. And so that addresses one of the concerns about neutron loss to xenon. That just comes right out of solution during the operation of molten salt reactors. It is also much easier to work on the fuel in its existing form. Molten salt fuel does not have to be chemically converted to something else in order to be processed like solid fuel does. Solid fuel, we have to turn it into something else. Molten salt fuel, we don't. So that's why I think it's very important to remember the merits and the benefits of molten salt and why molten salt is mentioned so often with the thorium fuel cycle. So this is the classic design for the molten salt reactor that came out of the Oak Ridge effort in the 1970s. It's what we call a single fluid reactor. All of the fuel components are mixed together in one very large unit. It's internally moderated by graphite stringers. Unfortunately, as was mentioned by Dr. Rubia, it is a rather complex reprocessing system in order to turn this one fluid reactor into a breeder reactor. It's got a number of different steps. It's got a number of different steps in order to go and make this a reality, involving the separation of that uranium from the fuel and protactinium separation, decay, and rare separation. A number of things that were mentioned earlier today. So I will just agree that it is a complex chemical undertaking in order to go and prepare and to turn one of these reactors into a thorium breeder reactor. Now, previous to the one fluid reactor work, there had been Oak Ridge studies done on what's called the two fluid reactor. And the two fluid reactor is fundamentally different in that it separates the fuel, the uranium-233 fuel in Flibe salt, from a blanket material, which is also Flibe salt carrying thorium tetrafluoride. Very similar to the fuel combination or the blanket combination that Paul just showed, except that it has beryllium in it, and it's not just lithium and thorium. The challenge of this two-fluid reactor design, though, is the internal geometry of the reactor, and to keep these two fluids separate from one another. This was an Oak Ridge design for that reactor. The advantage, though, of keeping them separate is the simplification that can be realized in the reprocessing step. And this is what I think is really worthy of consideration. Right now, we have to make an economic case for why should we consider thorium as a fuel source. We can go and we can mine uranium and we can enrich it and we can essentially burn out the small amount of uranium-235 in that. And you can put an economic quantification on the value of a gram of fissile material in the form of LEU. It's on the order of $10 to $15 out of the ground. That's what a gram of U-235 in that fuel represents. So if you want to make an economic case for why you're going to use the thorium fuel cycle, you better figure out how to turn a gram of thorium into fissile and and fission it for less money than that. Otherwise, despite the grand objectives of the thorium fuel cycle, nobody's really going to care from an economic basis. And so this is why we want to pursue radical simplification in the reprocessing. We want to make it as simple as we possibly can, but no simpler. With the two-fluid reactor, it is a rather straightforward thing to move the fuel that has been bred in the blanket out of the blanket through a fluoride volatility step and get it back into the core, which is where you want it. You want it in the core salt. And this has to do with the chemical properties of uranium and thorium in fluoride media. Thorium does not have a volatile hexafluoride. You can fluorinate it and fluorinate it and fluorinate all you want, and it will not change chemical state. It will stay thorium tetrafluoride. Uranium, on the other hand, does have a volatile hexafluoride. And this is why many of us feel that the uranium-thorium fuel cycle is a perfect fit with a molten salt reactor. This same trick doesn't work, by the way, in uranium-plutonium fuels. They both have volatile hexafluorides, and so you can't undergo a separation using the simple technique of fluoride volatility like you can with the thorium fuel cycle. So it's that radical simplification that we're pursuing. This two-fluid reactor design was also designed to be modular back when Oak Ridge was working on it. In fact, they were into small modular reactors before small modular reactors were cool. So these are some modern renderings we did to help us visualize their design and to understand its advantages and disadvantages a little bit better. These are two modules, two reactor cores with their heat exchangers, a steam turbine, or a steam preparation system that would be connected to a steam turbine. This is not the design we are personally pursuing, but we did it as a step to help us work on our design and to help us understand the geometries of this reactor better. Inside the reactor, these blue regions represent graphite channels into which the fuel salt is flowing. These green regions represent graphite channels into which just blanket salt is flowing. And these black graphite structures represent the reflectors. This is to give you an idea of what the internal geometry of Oak Ridge's two-fluid reactor design looked like. So we formed Flibe Energy, as I said, to help realize this goal of designing modular, two-fluid, molten salt reactors that implement the thorium fuel cycle, and also a response to the way our government expects things to be done in the United States, to be industry-led, to have a business case behind it, to go and make an argument for why private investment and private industry should be interested in these technologies. But our fundamental motivation is that we share the dream that was put forward by Dr. Alvin Weinberg long ago of a world set free by the use of thorium as an essentially unlimited energy source. And I know it was said earlier that thorium's not a miracle. To me, it is a miracle. It's a miracle that there's a material on Earth that has such remarkable energy density that even worthless dirt is transformed into an energy resource greater than the richest crude oil or anthracite coal or any other resource you can imagine. To me, that is truly a miracle. We're in Huntsville, Alabama. Many people don't know much about Huntsville, Alabama. Let me introduce the city a little bit. This is the city where Wernher von Braun and his rocket team set up shop in the 1960s. We're proud of the fact that we're the town that put man on the moon. It's a very high-tech community. It's also very well located within the United States. It has extensive river access to the Gulf of Mexico and to all the inland waterways of the U.S. We have a large international freight airport that has daily flights around the world, carrying freight straight to Europe, and connected to an extensive rail network. So we're very well positioned. We're also well positioned in the fact that damaging storms and hurricanes always peter out by the time they get to Huntsville. So we're protected from some of the extreme weather you might face on the Gulf. We're also fairly close to Oak Ridge National Labs, the birthplace of thorium and fluoride reactor technology. And the graphite reactor, that was where the first uranium-233 properties were calculated, where they realized the breeding potential of uranium-233. The first molten salt reactor, the aircraft reactor experiment, and of course the molten salt reactor experiment, which ran for almost 5 years and demonstrated the fundamental compatibilities of the graphite, the salt, and the Hastelloy material that contains the reactor. It was very successful. I've had the good pleasure of speaking with some of the gentlemen who worked on this project long ago. Now, because of our proximity to Oak Ridge, we can move things by river, and it's not too long of a drive. And most importantly, of the handful of folks that actually worked on the molten salt reactor program, they live generally in this area. And if you'll take them to lunch or go sit on the back porch with them, they'll tell you some stories about molten salt reactors and probably save you a lot of trouble and prevent you from making a lot of mistakes. So they're nice folks, but I'll tell you what they're not interested in. They're not interested in full-time work in this, and they're not interested in any money. You know, the youngest one is about 76, and the oldest one's about 88. So they're at a stage of life where this is their motivations are entirely different. One of the things we want to do with our more modern implementation of the molten salt reactor is to couple it to a gas turbine. And this is something that was really not considered during the days of the molten salt breeder reactor effort. They were going to couple it to a steam turbine. We think a gas turbine is the right step. There's a number of reasons. It addresses some of the issues that we've been concerned about with tritium migration, but it also gives us the potential to radically reduce the form factor that would be involved in a power conversion system. And this is a chart that originally came from MIT that gives you an idea of the size reduction that you can realize going from steam, it's 250 megawatt steam, down to closed cycle helium, 333 megawatts, all the way down to supercritical CO2. And we're looking with great interest in supercritical CO2. What these power systems lack, though, is a suitable heat source. These are not combustion turbines like we're used to in gas turbines. They have to be externally heated, and that's where a high-temperature reactor, like a molten salt reactor, shows great promise. Now, there was some degree of precedent for coupling a molten salt reactor to a gas turbine. In fact, one of the original ideas was to use a molten salt reactor to drive open-cycle air gas turbines and power a jet. So this is the crazy idea that kicked off the molten salt reactor. So there is just a little bit of precedent to using gas turbines. So how would our machine work? Well, the Flibe salt carrying the uranium would pass through a core where it would be moderated by graphite. It would increase in temperature, pick up enthalpy, exit the core, pass through a primary heat exchanger where it would transfer that enthalpy to a coolant salt. And this coolant salt, probably something like bare Flibe, no actinides in it, would pass in and out of the containment boundary of the reactor, and it would heat the gas that would then drive the gas turbine. The gas turbine, being a closed cycle, has to be both heated and cooled, and the waste heat from the gas turbine is of suitable temperature and quality that it could be potentially used to desalinate seawater. And that's another very exciting possibility, because you go to a lot of places in the world that are interested in nuclear energy, and they're just as interested in fresh water. And they're just as concerned about their water situation as they are about their electricity situation. So having a power conversion system that is suitable for desalination, I think, is a great advantage. Now let's talk a little bit about the fuel reprocessing, because this has been a topic of some degree of controversy today. The processing that we envision between the core and the blanket is to simply run a stream of fertile blanket salt that contains a small amount of uranium-233 that has been bred into a fluoride volatility column where it is contacted with fluorine or another fluorination agent, potentially nitrogen trifluoride, and then the uranium will come out of that solution as uranium hexafluoride, as a gas. Then that gas is reduced in another column in the presence of fuel salt, UF6, and hydrogen gas, and hydrogen will reduce that UF6 back to UF4, putting it back into solution and allowing it to return to the core. Now the core has been refueled by the uranium that has been generated in the blanket. The resultant of this process is HF, which can then be sent to an electrolyzer and split back into the reaction component. So this is a very, very simple approach to reprocessing the blanket. It involves two steps, neither of which requires any sort of cooling time or wait time. They're both rad-hard processes that can proceed immediately. In the event that we need to quench the isotopics of the system, well, in that case, we can actually add uranium-238 if we feel like we are about to lose physical control of the plant. That is a real option. Now, on the core side, similar processes take place. You use fluoride volatility to strip off the volatile fluorides, particularly uranium, and then you go through a distillation column that will separate the uranium hexafluoride from the other hexafluorides, or the other volatile fluorides. And then the salt, which has now been stripped of the uranium, goes to a vacuum distillation system. And in this system, the lithium fluoride and the beryllium fluoride are boiled out of the salt, leaving the fission products behind. That recycled Flibe salt then is recombined with the uranium hexafluoride in a reduction column. Same technology as here. So these, in fact, these are actually the same unit. So use your imagination here. They're really the same thing. And then that salt is returned to the core. So the outcome of this system is just fission product waste. We keep actinides in the reactor until they're consumed. And that's another very important distinction between having a liquid-fueled reactor and a solid-fueled reactor. We don't lose material when we take it out and have to dissolve it and reprocess it. If it didn't come out in reprocessing, then it's still in the blanket or it's still in the core. And we can realize a waste stream that consists entirely of fission products. We can also potentially realize a very efficient approach to converting thorium into U-233 and into energy by taking this approach. And these are simple steps. Fluoride volatility, in both cases, reduction there, and then vacuum distillation. So basically, 3 or 4 processes to get you a completely closed nuclear fuel cycle. Safety is one of the most important reasons to consider very seriously molten salt reactors. And this is because of the clever implementation that was demonstrated in the molten salt reactor experiment of the freeze plug and the drain tank. And what this simply was it was just a small port in the bottom of the reactor that was kept plugged by a frozen plug of salt. If all power was lost, that plug melted, the fuel drained. into this drain tank, and the difference between the drain tank and the reactor vessel was the reactor vessel was not meant to lose any thermal energy. The only place you wanted to lose thermal energy was to give it up in the primary heat exchanger. The drain tank, on the other hand, is designed to maximize the rejection of thermal energy to the environment. It does not have any graphite in it. So in this vessel, recriticality is impossible. And this is an important distinction when you have a thermal spectrum molten salt reactor. A thermal spectrum molten salt reactor has to have the graphite moderator of the core in order to sustain criticality. If it's drained into that drain tank, or if the vessel ruptures and it falls into this catch pan and drains in this drain tank, recriticality is fundamentally impossible. How do we keep the drain tank ready to go? Well, we actually use it as the decay vessel for fission product gases. So one of the processes that we need to deal with anyway keeps the drain tank in a ready state to receive the decay of fuel in case that needs to take place. So let me sketch out a little bit of a future here, thinking big. Here's what we're doing today with our nuclear approach. We are taking uranium and we are enriching it, and we're essentially putting that enriched uranium in light water reactors. And when we're done in the U.S., well, until recently, we were going to go and put it in Yucca Mountain. Now that's a little bit on hold. But in the process of doing this, we're also making plutonium, and nobody really has a good idea what to do with that yet. Our thorium stockpiles in our existing U-233 inventory in the U.S. are doing nothing. They're sitting around. If we look at what does the industry project we want to do, well, they're interested in saying, okay, let's go and potentially reprocess light water oxide fuel, perhaps make MOX, and then we would fuel MOX reactors using mixed oxides, and that would require a MOX fuel fabrication plant, which we could potentially send our weapons-grade plutonium to. But in the end, everything still ends up in Yucca Mountain. Again, no mission for the thorium stockpiles, and the existing uranium-233 inventory is disposed of. What we would propose is to use many of the materials that are otherwise going to go to waste and to incorporate them into a transition to a fully thorium-powered future. We would propose taking existing nuclear waste and fluorinating it, turning it from oxides into fluorides, and then separating out the bulk of it, which is just essentially low enrichment uranium, and sending that somewhere where it can be disposed of, and then removing plutonium and other minor actinides and using them along with existing reactor-grade plutonium, either in fast spectrum reactors, molten salt, or molten fluoride, or potentially molten chloride. And for the liquid fluoride reactors, the thermal spectrum reactors, we propose starting them, destroying our HEU stockpiles that way, creating new uranium-233, adding to this U-233 inventory, and then ultimately starting a fleet of liquid fluoride thorium reactors on this fine material, this U-233 that we heard recently is the best material to start the reactor on. In this scenario, we put both our plutonium, our HEU, our U-233, all to productive use along with our thorium stockpiles. I'll conclude with one of my favorite quotes from Alvin Weinberg. During my life, I have witnessed extraordinary feats of human ingenuity. I believe that this struggling ingenuity will be equal to the task of creating the second nuclear era. My only regret is that I will not be here to witness its success. Thank you very much for listening, and I appreciate your patience.
Yeah, thank you indeed very much for your perfect timing and even having 2 minutes. So the paper is open for comments and discussion. It was so perfect that nobody...
I think everybody's hungry and they want to go to dinner.
Well, we are in Europe, so
Can I ask...
8 to 9 o'clock is reasonable for dinner, not 7.
Please, your blanket.
Oh, sorry, excuse me. Okay, go ahead, and then you.
Your blanket, you separate the uranium from the thorium by the volatility. What happens to the protactinium?
In that configuration, the protactinium doesn't come out of the blanket until it decays to uranium-233.
So it stays in there even though it may get irradiated by more neutrons?
Yeah. One of the ways to mitigate that issue is to use a larger blanket inventory so that the average flux that any particular amount of blanket material sees is drastically reduced. So it's pretty cheap to add more blanket fuel or even to have an external holdup of blanket fuel. That's one way to really reduce otherwise the losses that you would have by having a lot of flux. And that's something you can do in molten salt reactors you can't do in solid fuel reactors. You know, you can reduce the realistic flux that a blanket fuel element will actually see over its lifetime.
Okay, thank you for that. Next question.
For a private company like yours, the funding is probably a problem. Can you comment about the funding of your program?
Yeah, we have been entirely privately funded. We've been incorporated now for 2.5 years. We have a variety of different investors in our company thus far, and are working to procure contracts that are going to allow us to go forward on this work. So, small but going forward.
I think there was behind, first to my left and then to my right. Yes. No, the first was not first. Okay, you turned it the other way around. No problem.
I think it's on.
Oh, it's on?
It's
Hello.
on.
Yeah. Besides the technical problems that need to be solved, it seems that in America in particular, we have a nuclear regulatory agency that is sort of like a certain football coach who said that winning isn't everything, it's the only thing, but the NRC acts as though safety isn't everything, it's the only thing. Are you making any headway in making changes, and if so, what changes, what hurdles do you have in this area, and what changes would you like to see in order to make it practically feasible to get underway building things?
Great question. We are making headway with the NRC. We have reached out to them, and they have assigned us a case number for our development activities. Also made it clear that further interactions will be billed at the going rate of about $270 an hour. So it is not an inexpensive thing to begin to engage with the NRC. That being said, through informal contacts with a number of NRC personnel, they have indicated a great deal of optimism. They, talking to some of them privately, they've said, this looks really safe. You guys have chosen a design that eliminates many of the issues that we are concerned with from the get-go. And even though this is very different than a light water reactor, thus far the response from the NRC personnel we've talked to has been cautious optimism and essentially saying, go forward. The NRC is happy to look at anything so long as you pay their billing rate. What they won't tell you is how long it's going to take, and I can kind of understand that. They have to take time, and they have to go through their evaluation process. Our job is to go and educate them on this design until they feel comfortable enough to issue a license, and that's fair, and we understand, and thus that is the direction we will go. We do realize, though, that this is going to require a lot of education. This is very different than a light water reactor in every way, but sometimes perhaps being different isn't all bad. If you can help them understand why this can achieve a level of safety that perhaps they've not been heretofore able to achieve, then...
Let's maybe stop this philosophy, how one has to handle US government organizations. We all know that they are quite difficult in all our countries. Is there a last scientific question? If yes, there is one last. Short, please, and short answer, please. And then, please do not right now, for this very last minute, leave the room. There will be one announcement by the organizer, which you should hear.
It's not a scientific question, but how much do you think it would cost to build a prototype, and how long do you think it would take to actually build one?
Two numbers. Two numbers. Just two numbers.
We're undergoing a feasibility study over the next 12 months that we believe will yield those answers. So come back next year, and we should have a good presentation to tell you on that.
It's not yet ready, the number. That's fine. Okay, let's close. Let's thank you.